Welcome to Season 2 Purdue University College of Sciences Superheroes of Science podcast. I'm Stephen.
And I'm Sarah. We will be discussing anything and everything related to science. If you have a science question, tweet it to us at Purdue SOS, and we will try and find someone to answer it for you.
Today on Superheroes of Science, we are on location in Stephen's office, and we are excited to welcome Gray Nearing. And Gray is a professor in Geological Sciences at the University of Alabama. And Gray, you're here with us visiting Purdue today.
Yeah.
Part of your schedule today was a public seminar that you delivered on, let's see, what role does hydrological science play in the age of machine learning?
Yeah, that's right.
Excellent.
Yeah, did you want to explain that to us? Because we read that and it's like, well, that sounded so cool.
It does sound really cool.
But I'm not sure what it means. But I know it sounds cool.
So hydrology is the study of water, and we look at water that's available to people, so water on land and fresh water. And mostly, hydrologists look at all kinds of water, oceans, atmosphere, land, but mostly on land. And I personally look at water on top of the land, so water that's available to plants and people, and in our streams and in our lakes and things like that. And we're finding more and more that we can use machine learning or advanced artificial intelligence to get a better understanding of where water is and where it's going to be in the future.
Oh, wow.
How does that work?
Right. I looked a little bit. So machine learning, you said it uses artificial intelligence. Does it just come through just lots and lots of data? What does that look like?
Yeah, so we keep track. We take lots of measurements of different properties of the Earth, and water constitutes several of those properties. So we have satellites up in space that measure the amount of water in soil moisture, the amount of water in vegetation, the color of the vegetation, which react to droughts and floods and things like that. We can actually observe floods from space using radar satellites. And so we look at all this water from space, and we also have groups of scientists, hundreds of scientists all over the world that have set up towers and different kinds of stations all over the world to measure the fluxes of water, the transfer of water from the land surface up to the atmosphere, and from the atmosphere back to the surface. And those are tied with the carbon balance and the energy balance at the surface. And so we monitor that all over the world, and then we try to build models that replicate what we see in the data. And then we use those models. We take those models and we train them, or we get them to replicate what we're seeing in the data, and then we turn them loose on the rest of the world to make predictions. And we predict things like where floods are going to be. So hydrologists will tell you if the Wabash River is going to flood, for example, tomorrow or in the next couple hours. And you might someday in your life get a push to your cell phone that says something like that. And so most of the governments in the world will do something like that, and they're using some sort of model, some sort of computer code underneath those that simulates the water cycle. So it's actually predicting what's going to happen in the water cycle, and it's using all of this data that we're collecting from NASA and NOAA and the U.S. Geological Survey are being fed into those models to make those predictions.
Wow.
Well,
How is something like that coordinated with the different, because you said NASA, NOAA, and the USGS. How does that even that's a lot of different data sets. So how would that get coordinated to be usable?
It's very political.
Is it really?
Yeah, absolutely political.
I did not expect that as an answer.
I did.
Yeah. So the great example of that, I'm from Alabama. The University of Alabama has the National Water Center, which is probably the main federal water prediction center in the United States. And that's mostly U.S. Geological Survey and the National Oceanic and Atmospheric Administration. And they run a model there. And again, a model is just a big computer code that's trying to mimic the way we understand the water cycle. And so they run this giant computer code on a very large supercomputer, and it produces predictions of river flows at 2.3 million points, reach a million pieces of places in streams around the United States every few hours. And so what it took to sort of build that center was a senator that wanted to put some money behind this project. The National Oceanic Atmospheric Administration and the National Weather Service have been tasked for several decades to produce flood forecasts. And the U.S. Geological Survey has always been the ones measuring the amount of water in our rivers in the United States. And so it really took people at the top levels of those agencies getting together and deciding that we're going to bring our people and bring our data and bring our money together and and build this national water model. So the national water model started making predictions in 2017.
Oh, fairly recent.
Yeah.
So do you have to look at like weather models, then take the output of that to put into your model, the hydrology model,
Yeah.
to make a prediction then?
That's exactly right. So you take the weather forecast that everyone can get, and these weather forecasts are coming from NOAA, National Oceanic Atmospheric Administration. And we take those, and basically we care mostly about the precipitation, the rainfall, and then those are fed into the hydrology model.
Wow. So you said there's like 2.3 million data points, or maybe I heard that number wrong, in different streams around the United States?
Yeah, so
And is that the USGS monitoring stations?
yeah, so there's 18,000 of those 2.3 million points are USGS monitoring stations.
Okay.
Okay.
The other 2.3 million points are where we don't have data, and we have to rely on the model to give us some idea of how much water is in the river. So there's 2.3 million points that could be flooding at any given point in time in the United States.
Okay.
And usually they're highly correlated. So if one spot on the Mississippi is flooding, another spot will be flooding as well. So you'll never just have one of those points. But yeah.
Does remote sensing help in any way? I know the USGS has certain like boxes where they'll get that, but are there other ways of getting that data?
Yeah, so it's a research project to ingest satellite data and remote sensing data into the national water model. But the national water model is only one major hydrology model in the world. Most major governments in Europe and Australia and North America and East Asia run some sort of water model, and a lot of those models ingest satellite data regularly. And some of those satellites are, back in 2015 I was on the SMAP. So SMAP is one of a NASA satellite, soil moisture.
Active soil moisture.
Active passive
Soil moisture. Yeah. Oh,
Yeah.
Soil moisture, active, passive.
thank you.
Yeah.
It's because Sarah and I are part of the GLOBE program.
Okay.
Which do you know the GLOBE program?
I don't.
Global Learning Observations to Benefit the Environment.
Okay.
It's NASA and NOAA are sponsors for that, and so that's a citizen science. The program started with just in schools, and it's students all around the world are collecting data. And hydrology data is one of the things they collect, and so we teach those workshops, and we have teachers who have students doing projects studying and collecting water information and putting that actually in the GLOBE database.
Cool.
That I don't know who all uses. I know other students do, and we're told different scientists use the actual ground verification of. Like when SMAP went up for the soil moisture, they contacted GLOBE schools in different places and asked them if they would do the galvanometric soil moisture protocols at certain times to help ground truth verify the satellite data.
The CalVal. Yeah. So one of the things we did in the early part of the CalVal is we would go out to different places around the world. So I personally went out to Australia, out in the middle of nowhere in Australia, camped out for 2 weeks, and we would walk in straight lines for several kilometers, and every 100 meters you'd stick a measurement device in the ground, and it had a GPS on it. And so as the satellite flew by, we'd have these ground measurements, and we spent 2 weeks just going up and down lines in middle Australia.
Oh, wow. So we're using like a soil moisture sensor?
Yeah, it's a little electronic probe that we stuck on the bottom of a PVC pipe, so we wouldn't have to bend over every time. And then we put the GPS on the top of the PVC pipe, so we just walk and stick it in the ground.
Oh, that's a smart way to do it. I like that. Because we have soil moisture sensors that we do in some of our lessons.
Oh, yeah.
And so, and obviously teachers use those and things too.
Yeah.
And so that's something that we know a little bit about.
Yeah,
Enough to be dangerous.
Right.
Not at your level. You can be a lot more dangerous.
Right.
Yeah.
That's right. Yeah. I can tell you stories.
Yeah. Well, we might want to hear some of those when the recording's off. But so while all variables, when we talk about this model, in taking the assumption there is a lot of data involved. Are you, of course, rainfall would be one. Then you're looking at all the way down to like permeability of soils, evapotranspiration rates, seasonal evapotranspiration rates. And so those are things we're looking at too, right?
Yep.
And if we have like large areas that ground cover change, and so are we looking at ground use?
Yes.
Different codes for that?
Absolutely. Yeah, and it is codes. So there's sort of a classification table of ground cover types.
The MUC codes? So you use that system?
We're using some USGS codes and some codes that came out of the University of Maryland, mostly. And there's vaguely, let's say 12 or 14 major ones. And they're things like urban, ice cover, water, bare ground, cropland, evergreen forest, deciduous.
Yeah, it's very similar to what the GLOBE program uses in their biometry protocols.
Okay, great.
And do they have the GLOBE Observer app where just regular citizens can go out and go through the calibration on it to kind of calibrate themselves and do ground cover protocols there for the program?
Right, and so if a particular piece of ground changes, like let's say someone builds a neighborhood, and so a particular portion of the ground goes from, let's say, shrubland out in Arizona to urban, so they built a neighborhood on that particular piece of the desert, we change that in the model to reflect that, or at least we try to. Of course, it's hard to see and make all those changes, but that's kind of the point of it. Yeah.
Now, are you to the point where the satellite data or pictures come in and then a machine looks at those pictures saying, oh, well, this is urban, this is, or are you still a person have to look at those? And
yeah, so somewhere deep in the processing chain, there is absolutely a machine learning algorithm that tries to go map from what the satellite's seeing to these land cover types. Wow. An example of that would be, and I'm not involved in this in any way other than downloading the data and feeding it into my hydrology models, but the MODIS satellite will produce every year, will produce a land cover map that changes every year. And so our machine learning models do take those. So the national water model that I mentioned earlier, I don't think it takes the updated MODIS product, although it might, don't quote me on that. But our machine learning models do take this in every year and kind of change what we see from year to year. Yeah.
So are places like, so I'm assuming environmental management places would be interested in the hydrology models, or is this getting to like insurance companies too?
Yeah.
Who all is using a hydrology model? Who's looking at that and why?
Yeah, so insurance companies do use them, and sometimes they develop their own hydrology models in-house. Yeah.
Oh, wow.
Yeah, so certainly some of our students go work for reinsurance companies that build these.
Okay.
But some other customers are people like reservoir operators. So if you have a hydropower dam, right, and you have a reservoir that's keeping the water, and so they have to decide when to release to generate electricity or when to keep it, when to release so that they have space so that to stop, if it's going to rain, they use those reservoirs to stop flooding, right? And so those companies, if they're privately owned or if they're managed by the Army Corps of Engineers, those dam and reservoir operators really need accurate stream flow predictions. So that's one example. Another example might be if the Nature Conservancy buys water from farmers, right? So they'll pay farmers to not irrigate their crops. And so they like to use satellites and models to sort of monitor that and make sure that the people that they're buying water from are sort of obeying the agreement and not irrigating their crops. There's actually quite a bit of uses. So another great example that we worked on when I was at NASA was the USAID, which is the federal agency that distributes aid to countries, international countries that need food aid. They like to know where droughts are going to occur and where water shortages are going to occur, because that helps them plan where to plan to put food aid, right? So some of the global models that are run at NASA monitor droughts in places like North Africa and the Middle East and things like that.
Wow.
It's really interesting.
I had no idea it'd be that big.
Right.
I mean, I guess you think that models running here just kind of looking at things here, but I didn't realize it was be that connected.
Yeah. One of the other big uses for the hydrology models they're the lower boundary condition. They model the Earth's surface for weather forecasts. So most weather forecasts have a hydrology model underneath that controls how much water goes from the land to the atmosphere. And so your weather predictions rely on this. And then, of course, all the climate models that are run by the Climate Model Intercomparison Project, the IPCC report, have hydrology models that are at the bottom of those as well.
Okay. And so that sounds almost, like a circular pattern.
Yes.
where you have a hydrology model that's a base for an atmospheric model.
Yep.
That in turn, we take that output for a hydrology model.
Yes. So they call it running in either coupled mode or uncoupled mode. Coupled mode means that actually the same piece of computer code runs the hydrology model in the atmosphere, and so there's actually sharing. The uncoupled means we take the atmosphere and we feed it into the hydrology, and usually you run them in uncoupled mode only when you care about the water, not when you care about predicting weather.
Wow. So I noticed part of what you were talking about was bringing is it students in that, so when they're learning, let's say about the water cycle or something, and then pairing that with this machine learning as well, what does that look like?
Yeah, it's hard. I mean, it's kind of hard in a couple of senses. One is that most, let's say, high school students or young college students don't have a lot of machine learning experience. You have to know how to write code, and you have to understand a little bit about machine learning. But at the graduate level, we get students that are really interested in this, and it's actually a really valuable skill. My students that do machine learning for water forecasting are recruited before they get their degrees. I mean, there's people, there's a lot of money to be made in this area, and it's just really just starting. So we're about, let's say, guesstimating about 5 to 7 years into the AI boom in the environmental sector. And so it's a great way to have a stable career that pays well, and also, you know, you can make the argument that it's adding benefit to society, right?
Oh, absolutely. But so if a student just now is hearing about artificial intelligence, like what do they need to be looking at, or what are some tips for them to kind of get their feet wet into learning about, you know, what should they be doing? What should we be guiding them to do?
Yeah, I mean, I would just love to see more high school students learning how to write code and learning how to manage a GitHub repository. So writing code is kind of like an art form, and it's something that you can do even if you don't have that class available at high school. If you do, you should take that class in high school for sure. But even if you don't, a lot of kids can get into it, and it's kind of like I see it personally as an artistic outlet, a creative outlet. And so there's a really great website called GitHub, GITHUB, okay? And it allows you to sort of store all of your coding projects. So you can go online and find interesting coding projects, and then you can post it to GitHub, which is sort of like social media for programmers. And you build friend communities there, and you share your code. And eventually, after you get through college, if you've done this for a long time, now you have this portfolio, very much like an artist's portfolio. And this is what employers look at when they want to know if they can hire you to be on their software development team, or on their environmental informatics team, or something like that.
That's really neat.
And not the first time we've heard that this calendar year.
Yes.
Last month we were in a session at a conference, and that's something that they suggested. One of the panelists suggested the kids do.
If I were to when I give my students, graduate students, undergraduate, one piece of advice, it's start a GitHub repository and make sure that you spend some of your free time learning how to write code and making it public on this repository, so that eventually you can show it to prospective employers.
And I just now heard about it. I know my son had told me about it before. But I don't know how many projects he was actually actively working on, but I know he had an account and stuff.
And there's great online resources. So if you don't know how to get started, you can take a class, like a Python programming class, open access. And then there's things like Kaggle, which will sort of give you lists of problems that can be fun to solve. And so you can kind of go online, and some of them are competitive. And so if you're really into it, you can kind of compete against people at your own skill level and things like that.
Well, for a high school student, what type of code would you suggest they
Python.
Python is okay.
There's no question anymore. I mean, people are
seniorize. You had the answer ready. Stop talking. Let me answer that.
No, everyone will have a different opinion, but the reality is that if you learn Python, you're safe. And it's also easy. It's also sort of intuitive. You don't have to learn it's much more intuitive than a lot of the other languages.
That's really interesting. Thank you for that advice.
So that's good input right there. That's good to know. What other classes are there? So we have coding that is very important. if someone in high school is like, wow, what he's doing is really cool, to be able to model the hydrology, to be able to understand and have ideas of, where floods could happen, and things like that. What are other classes that would be important for them to make sure that they look for and take?
Yeah, it's interesting. So my advice to especially young people is always build your foundations. So if you want to go, earth science is a great field to get into, right? There's a lot of job opportunities and it's rewarding, right? But if I were to give advice to high school students or even college students in undergrad, it's build your foundations. So build your understanding of statistics and math and coding, and those are your priorities. And then actually learning the earth science can come later, but you're better off building your foundations when you're young than you are trying to go directly into earth science and then realizing when you're in a professional career that you needed more of the basics. Yeah.
I see.
That's my advice. But on the other hand, you don't have to be an expert in math to go into earth science. And so it's a great STEM field in that aspect. So you can get as deep as you want into statistics or probability or calculus or algebra or computer programming. I mean, you can really go as deep as you want and be an earth scientist, but you can also be an earth scientist and that doesn't do calculus. So there's a lot of work, they're really valuable, important parts of the big earth science project that don't require math skills. And so it's a really interesting field to be in because people come into it for a lot of different reasons and a lot of different interests and a lot of different skill sets, and they get to work with a lot of people with a lot of different interests and skill sets. And you can kind of you can work outdoors, you can work indoors, you can work on a computer or in the laboratory. I mean, you can be interested in physics and chemistry and biology and ecology and mathematics. Earth science kind of brings everything together. And so, but again, if I were to give a student advice, probably it boils down to do well in math in high school.
I think that's really solid advice.
Yes, it is.
Well, speaking of that, how did you get your interest in science?
Yeah, it's a great question. And it was because it's a great question. I came out of my undergrad. I got a whole bachelor's degree with no idea what I wanted to do in life. And
I'm sure your parents were comfortable with that.
Yeah. That's right. Yeah.
As someone who has a kid in college right now, hope he's not listening.
I was a computer science major, then I was a theater major, then I was an engineering major, and then I finally got a degree in math. And I realized that I had no idea what I wanted to do, but if I went and took the basics, then I'd be able to go anywhere.
There you go.
And then earth science is great because there's a lot of opportunities. There's a lot of work that needs to be done. You can get funding. You can go to graduate school. You can go to private consulting firms. It's really easy to get a job, and it's good. I mean, it's all positive work for the world. I mean, you're adding value to the world, and so that was my story.
Oh, cool.
Nice, yeah.
No, I am surprised. I guess you have the earth science side, but I mean, you're really big on the data side. So I just really figured most of what you did would be at a computer. I didn't figure you'd be in the field work.
Yeah.
And so when you're like, oh yeah, you've walked through the desert with a GPS stick. Like, whoa, I did not. So I guess I didn't think of someone who's big into data science also get into some of the field work.
And you can build a career where you change that balance over time. So, I mean, what you're talking about is actually what we did there was collecting the data that we end up feeding into the computer in some sense. And you can have a whole career there. You can be in the USGS and do nothing but field work if you wanted to. And you could do nothing but field work for a while and decide it's time to go have a quiet life and sit in an office. And it's really easy to make this transition as well.
Oh, wow. So what's the coolest thing you've seen or done?
Coolest thing I've seen.
Yeah. I'll put you on the spot.
Yeah, that's great. Well,
I don't think I meant that. That's great.
Worked on a couple satellites that ended up getting launched. I didn't have a big role in them, but got to go to the launches and watch them go up and kind of feel like a small part in a big machine.
Yeah.
Wow,
That's cool. Yeah.
That would be cool.
Yeah.
That would be cool.
Yeah.
I don't know, though, walking
in Australia, I think that's
Australia.
I like that
for
one.
2 weeks. I don't know though, because did have to worry about like snakes and spiders
Oh,
and
yeah.
other things that would kill you.
For sure.
So
Oh,
yeah,
yeah.
see, I might abandon that one.
Yeah.
Might be braver than
Yeah,
me.
the emus, actually. We saw a lot of emus, and they're huge, and they're like pretty territorial.
Oh,
Yeah.
Did not
interesting.
expect that either.
A lot of kangaroos. We hit a
A
kangaroo.
lot of kangaroos.
Yeah.
You hit one?
Yeah, with our truck. It's
Oh,
pretty
no.
common. But
Oh.
yeah.
Huh.
A lot of kangaroos. Hundreds of them.
Oh,
Yeah.
did not. Well, I guess I never thought about that.
Yeah.
Yeah.
Around here in the Midwest, you just have to look out for the deer.
Deer.
Yeah. They're like deer. Yeah.
Okay.
Yeah. But a lot faster.
But a lot faster. They probably kick hard. Big old feet. All right. Well, we appreciate your time. It's pretty simple. So what we do.
Great.
Thanks
Yeah,
for
it's a lot
stopping
of
by.
fun.
Yeah.
Thanks for having me.
Yeah, absolutely.
Great.
Thank you for listening to our podcast.
Be sure to subscribe, rate, and leave a review
An outstanding
on
review.
iTunes or your preferred podcast player.
Tweet us your science
at
questions.
Purdue SOS.
Until next time, be super and remember,
You are someone's hero.
boiler up.
Hammer down.